So two really obvious things that we might want to do, having written these exponential functions, are give a value of the input variable and find a value of the output. That's easy, just throw it into the calculator. Or give a value of the output variable and find the value of the input. That's a little bit harder. We need to do some algebra. In particular, we need to solve for a variable that lives in the exponent. Here's an example of that sort of a problem. Suppose we know that the population of a small town increases by 3% every year. If its population is now 12,000, we'd like to know how long it'll take to reach a population of 18,000. And we want to give our answer as a decimal rounded to 2 decimal places. Even though this says what percent it increases by every year, it's presumably increasing all the time. It's not like a few hundred people move into town on January 1st every year. So fractional values of t make perfect sense in this problem. How would we solve this? Well, first we would write our exponential model. So our population as a function of time is our starting population of 12,000. The population is now 12,000 times our multiplier. If we increase by 3%, that means we have a multiplier of 1 plus 3%, so 1.03. How often do we do that? Every year. So we'll measure our time in years, and our exponent is just t. And we want to find t so that that equals 18,000. So now we have an exponential equation, and we need to solve it. So first we'll isolate the exponential by dividing both sides by 12,000. So 1.03 to the t is 18,000 divided by 12,000. Throwing that into the calculator, we see that it simplifies to 3/2. Or if we like decimals, we can say 1.5. Now we want to rewrite that in log form. T is the log base 1.03 of 1.5. Or in terms of the common log, the log of 1.5 over the log of 1.03. So now we can just throw that into the calculator. Algebra done. And we'll have the log of 1.5 over the log of 1.03. We get t is about 13.72. So about 13.72 years is how long it'll take for the population to reach 18,000. We can even check that, right? 12,000 times 1.03 to the power 13.72. The population will be 18,001 at that time. Very small amount of round-off error, but not very much. That's pretty good. Now, in this problem, fractions of a year made perfect sense. That won't always be the case. In some problems, time is in some sense discrete, or whatever our input variable is. There's something that makes us need to be especially careful with what direction we're rounding. And in that case, if we know we're going to round a lot, it makes sense to understand our question not as an equation, but as an inequality. So in this problem, Alice is depositing $150,000 in an account that pays 5.5% interest, compounded annually. Since it's compounded annually, interest is only added after a whole year passes, which means that we need to answer with a whole number of years. So we know we want a whole number to answer the question. And the chances of our algebra giving us a whole number are practically non-existent. So to see what whole number we want, we need to take into account that is at least. Is at least 2,500 means the value, which this is compound interest, we're going to call it P for principal, P of t is greater than or equal to 2,500. Right, if we have $7,000, that's okay. But if we have 2,400, that's no good. The amount we have has to be greater than or equal to 2,500. So our P of t, we start with 1,500, and then we multiply that by 1 plus the interest rate over 1. So 0.055 over 1 to the 1t. And we want that to be greater than or equal to 2,500. So 1,500 times 1.055 to the t is greater than or equal to 2,500. Divide both sides by 1,500. We have 1.055 to the t is greater than or equal to, working that out on the calculator, we get 5/3. I'm going to leave that as a fraction because it doesn't give me a very nice decimal. So my base is greater than 1. I don't need to reverse the inequality. I'll get t is greater than or equal to the log base 1.055 of 5/3, which is the log of 5/3 over the log of 1.055. Throwing that into the calculator, we'll get the log of 5/3 over the log of 1.055. So that's 9 and a bit. We need our t to be greater than or equal to that, so we're going to have to round it up to 10. So how long does it take the value to be at least 2,500? 10 years. Choosing a whole number because only whole numbers make sense in this story. And we chose to round up, not because this digit is a 5. We don't care about that. We chose to round up because we want to be greater than or equal to this number.